Hello everyone, welcome to CS 350. This is Karthik Gopalan. In this lecture, we are going to discuss Introduction to Virtual Machines and more generally about virtualization technology. Most of this material is from the book by Smith and Nair on virtual machines, primarily chapter 1. There's also a significant material from Andrew Tenenbaum's book on modern operating systems. So, what do we mean by virtualization? The notion of virtualization refers to taking any set of real system resources and making them appear to be a set of virtual resources. For example, you might take a single physical computer and using some additional levels of software indirection, you can make them appear to be like multiple virtual machines. There are various types of virtualization. One-to-many virtualization refers to the type of virtualization that I just described. You take one physical resource and make it appear as if there are multiple virtual resources. For example, one physical machine may look like multiple virtual machines. One physical disk may look like multiple virtual disks. Or you could take a physical network which is distributed in nature and you can make a physical network appear like they are multiple virtual networks sharing the same physical infrastructure. There is also many-to-one virtualization. In this case, we are going in the opposite direction. We may have many physical resources and you might want to make it appear to the user such as there's only one virtual resource. For example, when we discussed the RAID concept, redundant array of inexpensive disks, there we were taking multiple physical disks and using a RAID software or RAID firmware, we were making it appear to the user as if it's one single virtual disk with certain reliability, availability, and throughput properties. You can apply the same concept to physical machines. You can take multiple physical machines that are connected by a network and make them appear using some distributed software. They can make them appear as if they are part of one virtual machine. And similarly, you can apply the concepts to networks and so forth. So, and taking this further, you can have many to many virtualization where multiple physical resources can be made to appear as multiple virtual resources, but using some sort of a transformation between the virtual and the physical layer. So here's an example of disk virtualization before we move into virtual machines. Let's say you have a single physical disk. All right. Now you can write a piece of software that can make this uh, physical disk appear as if there are multiple virtual disks on the system. So one way to do this is shown in the slide. You can use the standard system call interface and create files in a file system. So operating systems already provide you a file system. So using the file system, you can create two separate files, and on top of this file, you can write a piece of software that makes this file appear as if it's a virtual disk. For example, if you format the virtual disk, those operations would be transformed into formatting operations on the file. So different users can pretend they have different virtual disks, but in reality their operations go through two different files that reside on a common file system, which is managed by the same operating system, and finally the I/O operations are committed on a common physical disk. So this is an example of one-to-many virtualization where one physical disk is made to appear like multiple virtual disks. And of course it's very inefficient because of the use of file system, but you can optimize this indirection by including the virtualization software right in the operating system. You can bypass the file system layer for a more efficient implementation. So now we get to the topic of virtual machines. Virtual machine is basically a logical or emulated representation of a full computing system environment. So by that we mean various resources that you see in a normal computer, the CPU, the memory, and the I/O operations that that a user may want to perform. So the way virtual machines are implemented are by adding an additional layer of software to the real machine that provides this illusion of a virtual machine. There are various uses of virtual machines. The most uh, popular use that you might be familiar with is to run different operating systems side by side. For example, you might run Linux in one virtual machine and Windows in another virtual machine. Um, in enterprise environments, you might use uh, virtual machines for isolation purposes. For instance, different users may have their own virtual machines that share a common physical server, and so forth. Like there are many applications. For example, you might use it to enhance security by running untrusted or malicious code in a virtual machine that can be thrown away after use. You can migrate virtual machines as they are running from one physical machine to another, or you can use virtualization environment for testing and development. You might want to test an environment for which you don't have a physical machine available, so you create a virtual machine with the same properties for your testing purposes. So we'll be revisiting many of these applications throughout the lecture. So let's just revise some of the computer system interfaces that we have discussed throughout this course. So the, the, the key interface in this figure is the line in the middle that's labeled as ISA, or Instruction Set Architecture. That's the ISA is the hardware software boundary which separates which allows software layers, software stack to interact with the underlying hardware, execution hardware. So uh, so we'll mainly focus on the software stack here. So so the ISA itself has two parts: the user ISA and system ISA. These are basically instructions, their format, operands, and so forth, that are specified by the hardware manufacturer. The system ISA is the set of instructions that only an operating system can execute, whereas the user ISA is the set of instructions that any regular program can execute, even a non-privileged program can execute. The operating system provides an interface called the system call interface, syscall interface, which is labeled 3 in this figure. User applications or libraries uh, that want to do privileged operations, they request the operating system to do these privileged operations through the system call interface. So the system call interface and the user ISA 3 and 7 together, they constitute the application binary interface, or ABI. So it's important to understand the interfaces ABI and ISA, because the type of virtualization we are able to do depends upon which level of interfaces we are talking about. So based on the interfaces we just saw in the previous slide, there are two types of virtual machines: process virtual machines and system virtual machines. Process virtual machines virtualize the ABI. ABI is again the combination of system call interface and the user ISA. The process VMs are also known as runtimes because they represent the runtime environment, the environment seen by a process during execution. So these virtual machines usually virtualize the environment seen by a single process. They are virtualization environment for a single process. So these runtimes start when the process starts and they terminate when the process terminates. Since the ABI is being virtualized, the virtualization software basically hides the ABI, and whenever application performs certain operations, these are translated into the underlying ABI provided by the operating system and hardware. On the other hand, you have system virtual machines, which virtualize the entire instruction set architecture, or ISA. So here the virtualization software is also known as the hypervisor. Hypervisor is the first layer of software that boots up when the machine is powered up, and it stays up throughout the lifetime of the machine. And the virtualization software, the hypervisor, provides a virtual execution environment for the entire software stack, including the operating systems, libraries, all of its applications, and so forth. So Uh, unlike process virtual machines, system virtual machines, the hypervisors, they run as long as the physical machine is alive. So, let's look at some classifications of process virtual machines. The traditional processes that we have learned in this course are themselves, you can think of them as a runtime for the programs that you execute. So multi-programming operating system provides a virtual execution environment for each process. Each process thinks it has its own CPU, or if you have run multiple threads in a process, it thinks it has multiple virtual CPUs, and there's a virtual memory address space associated with the process. And in order to access the disk, there is a file system abstraction that's provided to the processes. Uh, so moving to more specialized runtimes, there are emulators that convert that perform translation from one instruction set architecture to another instruction set architecture. So for example, you might have a program that runs on x86 ISA, but then you want to run it on a machine which has a different ISA, for example, an alpha ISA. So you can basically write an emulator or a runtime that translates from x86 ISA to alpha ISA. Every time the program executes an x86 instruction, it will be converted to an alpha ISA by the runtime. So an example of such a system is the digital FX32 emulator, which allowed the Windows NT operating system to run on alpha ISA architecture, and it allowed the x86 applications to run on the alpha ISA without any modifications. So you were running traditional x86 binaries, but every time they would issue an x86 instruction in the user ISA part of the system, they would be converted into the alpha ISA by the runtime. So in contrast to emulators, there are other types of uh, runtimes called optimizers. Here you don't convert from one ISA to another. The source and the target ISAs are the same, but the job of an optimizer is to perform some efficiency enhancing operations on the code. For example, they might make your code run faster, they might utilize memory better, or they might improve the security properties of your program, such as by detecting buffer overflow attacks and so on. So optimizers are also a type of process virtual machines, except that their primary job is to do optimizations and make the programs run better. Then there is a category called high level language VMs. These are similar to emulators. Here the source and the target ISA are different. So the program operates against one ISA and it's converted into another native ISA by the high level language virtual machine. But the difference is that the source ISA seen by the program is a virtual ISA, which means that there is no physical machine that supports that type of ISA. And a common example is the Java virtual machine, Java programs. These Java applications are written against a special ISA called a bytecode, which is a stack-based virtual machine. When you run a bytecode application on a Java virtual machine, the JVM converts the bytecode into the native platform's instruction set architecture. So you can take your Java bytecode program to any machine having any ISA, and the Java program would just work without any problems because the JVM converts the instructions to the underlying ISA. So there are two types of emulators. There are interpreters and there are dynamic binary translators. Interpreters are slow, dynamic binary translators are fast. The reason interpreters are slow is because they take one instruction at a time, translate it to the native ISA, and execute it. Basically, they do fetch, decode, execute. So they or fetch, emulate, execute, fetch, emulate, execute. So every instruction is fetched, emulated, and executed on the native instruction one at a time. Dynamic binary translators, on the other hand, they take blocks of the source instructions, convert them all in one shot, and then execute them on the native platform. So by doing translation on blocks of code rather than one instruction at a time, dynamic binary translators are faster. But as a result, dynamic binary translators are also more complex. So we will not get into the detailed discussion about the differences between them here, but it, it suffices to know for now that dynamic binary translators uh, are more sophisticated and can do more optimizations so that they get better speed ups than simple interpreters. So now we will move to system virtual machines, which is the focus of this lecture. So in system virtual machines, we are providing a virtualized execution environment for the entire software stack, right from the operating system all the way to user level applications. A system virtual machine is also known as a virtual machine monitor. You might find minor differences in terminology on the internet, but uh, basically VMM and hypervisor are used to mean the same thing. Uh, so hypervisor can be thought of as an operating system for operating systems. So effectively, the design of a hypervisor very closely follows the design of a traditional operating system. It has to manage physical resources, and it has to provide an execution environment for rest of the software running on top of it. So uh, so in this example, in this picture, you have the hardware on which a hypervisor runs, and then there are three virtual machines running. Each virtual machine has its own operating system, which is called a guest OS or guest operating system, and each guest operating system supports its own processes. There are many applications on top of each guest OS. So so the way guest operating systems work is that whenever the guest OS wants to do a privileged operation, it will execute a privileged instruction. But since guest OS is not the most privileged software in the system, the instructions would be trapped by the hypervisor. The hypervisor will look at the privileged instruction and then it would emulate that instruction on the underlying hardware. So there is a trap and emulate mechanism that the hypervisor is implementing. So if the hypervisor wants to remain completely transparent, if it wants to make the guest OS believe that there's nothing else running under the guest OS, then hypervisor has to implement trap and emulate very faithfully. So you can, in a full virtualization environment, the guest OS can run without any modifications, and hypervisor would silently trap and emulate its privileged instructions. On the other hand, sometimes hypervisor can make itself visible, and the guest OS can more directly interact with the hypervisor. So you don't pay the overhead of trap and emulate. So there are various types of hypervisors. Type 1 hypervisors are also known as classical system VMs. These hypervisors, they execute directly on the hard on the bare metal, and they execute natively on the host ISA. When the machine is booted up, the first thing that powers up is the hypervisor, and then the hypervisors can spawn multiple virtual machines and manage them during their runtime. So uh, so hypervisor directly controls all the hardware. It needs to have all the necessary device drivers to control the hardware, and it uses the trap and emulate model that we just discussed in the previous slide. Some common examples of type 1 hypervisors are KVM virtual machine, the kernel virtual machine KVM, and the VMware ESX server. There are also other hypervisors called type 2 hypervisors or hosted virtual machines. Here our goal is to make the hypervisor simple. So one way to do that is to utilize an existing operating system as a host operating system. The first thing that starts on the host OS is on the bare metal is a host operating system such as Linux or Windows, and the advantage of this host OS is that it already has all the device drivers that you need to interact with the hardware. It has all the complex memory management functionality, CPU scheduling functionality, protection, and so forth. So all that the hypervisor has to do is just create the virtual resource abstraction for the VM. So for example, virtual CPUs, virtual memory, virtual IO devices, and so on. So this way, the hypervisor itself can be very small. The hypervisor can be inserted as a kernel module in the host OS, and there will be a small part of the hypervisor that runs in the user space, and you can instantiate VMs and run them uh, as if they are regular processes on the host OS. So so this type of hypervisor has a bigger footprint because the entire host OS is now part of the trusted computing base. So essentially, the hypervisor takes over the host OS and takes over the key operations of CPU scheduling, memory management, and so forth. So VMware Desktop Client, VirtualBox, all these are examples of Type 2 hypervisors. Then there's a third category called para-virtualized VMs. Here we want to have more efficient interaction between the guest OS and the hypervisor. So we want to move away from the trap emulate model to a model where the guest operating system can tell the hypervisor what it wants to do with the hardware. So just like normal processes, when they want to do certain privileged operations, they make system calls to the operating system. Similarly, guest operating systems can be modified so that when they want to do certain privileged operations, they make hypercalls to the hypervisor. So, uh, so, 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 so a hypervisor has to expose a hypercall interface. The guest operating systems can invoke the hypercall interface, and then they can utilize the hypercall interface uh, to communicate more efficiently with the hypervisor. Thus, you can save a lot of overhead by getting rid of the trap and emulate model. But the disadvantage, of course, is that you have to modify the guest OS. If you don't have the source code for the guest operating system, uh, then para virtualization will not work. So whole system virtual machines, as the name suggests, they basically pro perform emulation plus provide a system virtual machine environment. An example of this is the virtual PC. Here, the earlier Mac Mac OS systems from Apple, they used to run on a special processor called a PowerPC processor. And the ISA for PowerPC was different from the ISA for x86 or Intel processors. So uh, so the virtual PC basically performed emulation. You could run standard Windows operating system and its applications inside a virtual PC, and their execution would be emulated to the underlying Mac OS ABI, which consists of Mac OS system calls and the PowerPC user ISA. So uh, finally, we want to discuss a special category of hypervisors called co-designed VMs. Here, the hypervisor is designed closely to the hardware. You might have a special type of a hardware, and the hypervisor is designed very closely to work with that hardware. An example of this is Transmitter Crusoe. This was a chip designed by a startup company which had an ISA called VLIW, or Very Large Instruction Word ISA. The uh, However, since there were no operating systems that were using very large instruction word, so the designers of Crusoe also wrote a hypervisor that would allow standard x86 operating systems and binaries to run on their processor. So in this case, the hypervisor was performing a translation from x86 as the source ISA to VLIW as the target ISA. And this hypervisor was built into the hardware, or rather as a firmware, so that the guest OS and the applications were unaware of its presence. So this is an example of a co-designed VM. The purpose is to run just a single virtual machine, but on a specialized hardware for which the OS and the applications were not designed. So here's the taxonomy of different virtual machines we have discussed. There were two types of virtual machines: process VMs and system VMs. And within each of these, there are either same ISA VMs or different ISA VMs. And within that same ISA process VMs, we have standard multi-program systems, dynamic binary optimizers. Under different ISA process VMs, we have dynamic binary translators, and high-level language virtual machines. And under same ISA system VMs, we have type 1 classical VMs and type 2 hosted VMs, then para-virtualized VMs, and something called hardware virtual machines, which we did not discuss in this lecture. Under different ISA system VMs, we have either whole system VMs or co-designed VMs. So this is an example of the various combinations by which you can use virtualization. For example, you could have a core-designed virtual machine running on a VLIW processor. The hypervisor in this case is called a code morphing hypervisor, which allows you to run a Windows operating system and its applications. Within the Windows OS, you might run a VMware hypervisor, a hosted VMware hypervisor, which then within that virtual machine you can further run a Linux operating system that uses the x86 ISA, and within the Linux operating system you can run a Java virtual machine which allows you to run Java applications. So finally you have Java applications running on the VLIW processor, but through multiple levels of indirections. So there are various things you can do with system VMs. You can either do optimization and emulation, where a single VM is run by the hypervisor, but the job of the hypervisor is to either emulate the source ISA to the target ISA of the native machine, or it can do some optimizations to make the VM run better or more securely. Or you can do replications, where you can run multiple instances of virtual machines on the same physical machine. And you can also do composition, almost like plug and play, where you can run uh, one hypervisor on top of another hypervisor and VMs run on top of that in a nested fashion. So, uh, so next we will look at how individual resources are virtualized in system virtual machines. We'll look at CPU, memory, and IO virtualization. So let's start with CPU virtualization. Here the goal is that every VM should see a set of virtual CPUs. So when a guest operating system fires up, it normally asks the BIOS like how many CPUs are there, what are their properties, and so forth. Similarly, a hypervisor has to provide this information for a guest operating system. So, so the key problem here is that when uh, the guest operating system uses these virtual CPUs to execute privileged instructions, these instructions must be trapped by the hypervisor and emulated. You do not want guest operating systems to access shared hardware resources directly because it can interfere with other virtual machines on the same system. There are hardware extensions provided by modern architectures. For example, Intel provides VTX, virtualization technology VTX, and AMD provides the AMD-V technology. So the hypervisors can use these technologies to speed up the trap and emulate traditional trap and emulate model of virtualization. In particular, these technologies can let the hypervisor and the guests agree on what instructions would be trapped and emulated and which instructions would be directly executed without trapping. So with hardware virtualization support, CPU virtualization overheads can be significantly reduced. So here's a figure that shows this trap and emulate model. Whenever a privileged instruction is executed by the guest OS, a trap will occur. This trap will be handled by a dispatcher inside the hypervisor. The dispatcher routine will examine the instruction that caused the trap, and based on the type of the instruction, different interpreter routines can be called. So the job of each interpreter routine is to emulate the effect of the corresponding instruction. So on the second figure, this shows how a specific privilege instruction is emulated. This is a load program status word which tries to change the privilege level of the CPU. So when that privilege instruction is executed by the guest OS, a trap occurs which transfers control to the hypervisor or the VMM. Within that, there is a dispatcher. Dispatcher then looks at the instruction. It determines it's a load program status word instruction. Then it would transfer control to the load program status word routine, which then emulates the corresponding instruction. Once the instruction has been emulated, you want to jump back to the guest OS. So at that point, the controller is returned back to the instruction that follows the load program status word instruction. So this is just a very simple example of the trap and emulate model, and this mechanism can be speeded up in various ways by using VTX or AMDV technologies. Another thing we want to pay attention is how operating systems maintain control over the CPU resource. So this, so here the problem is similar to standard operating systems. Let's say that you have a process that's constantly running CPU bound jobs and it's not yielding the CPU back to the operating system. In this case, after a certain time, the operating system may want to get the control of the CPU back. So the way this is done uh, by both operating systems and hypervisors is that there's usually a timer hardware that comes with the CPU. The job of the timer is to fire every so often and inject an interrupt into the CPU. So when a timer interrupt is injected into the CPU, the operating system gets control and it executes a timer interrupt handling routine. And in the timer interrupt handling routine, you can insert logic that that decides whether the current process should continue executing or another process should execute. So similarly, when a hypervisor is managing multiple virtual machines and it wants to take control of the CPU from one of the virtual machines, the timer interrupt gives the hypervisor an opportunity to regain control of the CPU. So, so in the figure shown, you have an active VM that has control of the CPU and it's not giving up CPU. So at some point a timer interrupt occurs, which then transfers control to the hypervisor. Hypervisor would then save the state of the previous virtual machine, including CPU, registers, program counter, and so on. Then the hypervisor determines what is the next VM to be scheduled. Uh, and at that point, the hypervisor may schedule another timer interrupt if the timer interrupts are aperiodic, or or if the timer interrupt is periodic, then you don't have to do this operation again and again. Next, you have to restore the state of the next VM. What that means is you have to restore the MMU state, CPU state, program counter, and so on. And then you would jump to the location in the guest OS by and start executing the guest operating system instructions. So this is a standard context switch operation. The only difference is that from traditional operating systems is that here you are switching from one virtual machine to another virtual machine, and hypervisor is the one performing the context switch. Next, let's look at memory virtualization, how memory virtualization for VMs is different from traditional VMs. So there are two figures shown here, the tradition for one for traditional virtual memory and one for the virtual machines that we are discussing. The traditional virtual memory that we discussed, there you had processes which saw the view of virtual memory address space. So you were doing translation from virtual address space to the physical address space, and there was a single page table that allowed you to do the translation from virtual memory to physical memory. Now with virtual machines we have one more layer of indirection. You have regular processes that are executing inside the guest operating system, and then there are several guest operating systems that execute on a hypervisor. So the first level of memory translation is from the virtual address space to a guest physical address space. A guest physical address space means the view of the physical memory seen by a guest operating system. And then the second level of translation is from the guest physical address space to the physical memory. Here, here the hypervisor needs to perform translations from the guest physical address space into the physical memory. So essentially you need two levels of page tables, one for the first level and one for the second level. The modern CPUs have support for two levels of page tables. So MMUs in modern processors recognize that virtual machines have two-level memory translations. So the entire memory translation from the first level to the second level is done in the hardware. In some older processors, they supported only one level of page table, so you did not have two-level page table required by virtual machines. So in order to accommodate virtual machines in those systems, people used to do something called shadow paging. And even today, some of these systems do use shadow paging for various purposes. Shadow paging means that you take you still have two levels of page tables, but in software. And when you want to schedule a virtual machine, you would compress the two levels of page tables into one level of page table called a shadow page table. And the shadow page table would be the real page table, which would be installed in the MMU for use during the VM's execution. So, uh, so this is the summary of memory virtualization for VMs. Traditionally, you have single level page tables, but for uh, virtual machines, you have two levels of page tables: the traditional page table and then a second level page table. The second level page table is known by various names. For Intel processors, it is known as EPT or extended page table, and for AMD processors, it's known as NPT or nested page tables. Finally, we want to talk about I/O devices. Virtual machines need virtual CPUs, they need virtual memory, but they also need to get data in and out of the system. So for that, they need access to I/O devices. The job of the hypervisor is to share physical I/O devices among many virtual machines. So as a result, uh, the the hypervisor needs to provide virtual I/O devices to each virtual machine. What that means is that each VM thinks it has a virtual disk, but in reality, its virtual disk may be shared with other VM's virtual disks on a single physical disk. Or it may see a virtual network card, but then in reality, its virtual network card is shared on a single physical network card with other VMs. So hypervisor has to somehow provide this illusion that each VM has its own virtual device. There are various ways in which device IO virtualization can be done. There are primarily three ways. One is device emulation. You can take a real physical device and then provide an identical replica of it in a virtual form. For example, you might have, let's say, a Broadcom a network card on the physical device, and you might provide a Broadcom network card as a virtual device to a VM. In this case, whenever the guest OS tries to access the virtualized network card, the guest hypervisor would have to trap those operations and emulate the IO instructions on the real physical device. Generally, this is really low level of device IO virtualization. It's very hard to reverse engineer uh, physical devices and to virtualize them, because just because there are so many manufacturers, so many makes and models of these hardware devices. Another option is called para-virtualized devices. Here the idea is that instead of providing an identical replica of a physical device with belonging to a specific make and model, instead we provide a very simplified virtual I/O device. The virtual I/O device requires a special device driver which will be inserted into the guest OS. So, so, so this way the interaction between the guest OS and the hypervisor is simplified. There's usually a front end for the virtual device driver that sits in the guest OS and a back end for it that sits in the hypervisor. And the front end and the back end talk to each other using very simple producer consumer buffers. And finally, even with virtual IO devices, there's an extra level of overhead for the front end and the back end to talk to each other. So as a result, some platforms allow virtual machines to directly access the physical device. So if you have, let's say, many hard disks or many network cards, you can assign one physical device to each virtual machine. For example, every virtual machine can get its own network card to communicate over the network. In such cases, the hypervisor can configure special hardware to permit each VM to access its talk to its physical device directly. This mode is called direct device access, and this is the fastest option to perform IO operations. Here you're not virtualizing the IO device, rather you're providing direct access to the physical device. but it needs special hardware such as IOMMU and certain hardware extensions such as VTD technology. So this brings us to the end of the lecture on virtualization. If you're curious to know more information about this topic, feel free to talk to me.